Okay, welcome back on the final leg here. Lecture number 13, and we are going to look at how we use those logs that we've learned about in the previous chapter. So we're going to look at logarithmic equations, and next time we're going to look at logarithmic applications. So we're going to look at how we handle logs in mathematical expressions, essentially. So we're going to write the equations in logarithmic and exponential form and then use them as tools, and a little introduction to using the calculator to solve logs. So if we take a look at logs in exponential form, logarithmic equations can be solved either in logarithmic form or in exponential form. And you can see by the chart here, the table, the two ways that the information can be conveyed. In log form, log n equals x. In exponential, 10 to the x equals n. And the natural log then, the natural log of a equals b, or the e to the b equals a. So logarithmic equations then can be solved directly when the exponent is unknown. So if we look at an example here, if we have a value of log of 73 equals t, all we have to do is take the common log of 73 and we have solved for t, which might be a helpful term in a larger or more complicated expression. Changing from logarithmic to exponential form when a number is known. Again, if we take a look at an example, our example here says the natural log or the common log of y is equal to 4.73. So we don't know what that number is that we're trying to solve for. But if we use the exponential form by taking the value of the exponential to both sides of the expression, so if we take 473 and raise 10 to that value, that ends up becoming y. In essence, what we've done is we've taken the inverse log of log, which cancels it out, so we're left with y. So y equals 10 to the 4.73, and now when I run that value through my calculator, I can then solve for y, 5.37 times 10 to the fourth. It's a pretty simple operation. If you haven't done it before in the past or it's been a while, just doing it a few times, you'll get used to going back and forth between logarithmic form and the exponential form. So if we consider an equation here that we might encounter in a problem, solving for the unknowns then involves common logs. So if we are given a value, x equals the log of 250, and we want to solve for x, again, all we have to do at this point is take the log of 250, and we have 2.40 as our answer. That's the end of it. You don't have to go any farther. In another example, consider equations we might encounter in problem solving that involve the use of common logs. Given the log a equal to 7.83, so in this case, again, if we take the inverse log or turn it into an exponential on both sides of the expression, now the inverse log of a log just leaves a. The inverse log of 7.83 is just raising 10 to 7.83. Put that value in your calculator. Typically, it's a keystroke of entering a value of 10 to the x. If we look at my Hewlett-Packard catalog, 10 to the x, and I would just enter the value 7.83, 10 to the x, and what I get back then is 6.76 times 10 to the 7th. And you're done with the problem. That's it. Another example, what if I have a leading term? X times the log of 3 is equal to the log of 104. So now in this case, you just treat it mathematically like we've done handling at algebraic expressions. X is in essence, an unknown value. So I just divide both sides through by the log of 3 so that I get x equals the log of 104 divided by the log of 3. Take the log, the common log of the numerator and the denominator. I get 2.02 divided by 0.477, or a value of 4.23. In this case, the next example, we're going to solve for x. We have some unknown x raised to the value of 3.6, and we know that it's in solving that, had we known x, we would have a value of 85. Well, in this case, again, all I have to do is take the log of both sides of the expression, and you'll notice here the exponent on the x comes down as the leading term. So it's just a matter of bringing 3.6 down in front of the x after we take the log of both sides. So now we have a value that has an x term in it, the log of x. That becomes the value we're trying to solve for. So we move the 3.6 to the other side of the expression, to the right side, by dividing both sides through by 3.6. Taking the log of 85, I get 1.93 divided by 3.6, and we have a value then of 0.536. But at this point, we still don't know what x is. We've got the log of x, so now we take the inverse log of both sides. So that means raising 10 to the 0.536 equals x. The inverse logs kills the log, and x then is equal to 10 to the 0.536, or 3.44. Okay, let's look at another one, a little more complex. We have 3 raised to an exponent of 1 minus x equals 12. So when we take the log of both sides and bring that exponent down in front of the log, now I have 1 minus x as the leading term times the log of 3 equals the log of 12. I can move the log of 3 to the right side of the expression by dividing both sides. And now I have 1 minus x is equal to the log of 12 over the log of 3, which gives me 1.08 and 0.477 equal to 2.26. Now it's just a matter of taking the 2.26, subtracting it from the left side, and I get a value of x equal to minus 1.26. So it's all of these arithmetic and algebraic manipulations that we learned in the first handful of chapters that we are now using as the tools to solve these types of problems. Okay, and another one here. We've got a fraction that becomes an exponent. So 27 raised to the power x divided by 3 is equal to 18. So we got to figure out, how do we get that x out of the exponent and into the expression? Well, the first step we do is we bring that x over 3 out of the exponent and down to the front by taking the log of both sides of the expression. So now I have x divided by 3 is equal to the log of 18 and divided by the log of 27. Solve for those two values, I get 0.877. So the last step then is I'm going to take the 3 out of the denominator, multiply it through by both sides. So now I have 3 times 0.877, or 2.63, as our solution here for x. Okay, next example. If I have a value here where I have a log, we're going to take the log of a fraction, and it contains the unknown x, so that we can solve for the value of x. So the recommended solution here, the first thing we do is take the inverse log of both sides. The inverse log says that we're going to raise 10 to that 4th power, and we're left with x over 100. So now x becomes 100 times 10 to the 4th, or 10 to the 6th. Again, it's always best to put your answers in scientific or metric engineering notation. Solving for x. Now we've got the x in the denominator here as a log. So 8 equals the log of 200 over x. Again, we're going to take the inverse log of both sides. In doing so, we have 10 to the 8th is equal to 200 divided by x. I can multiply both sides through by x to get the x on the left side of the expression. If I divide through then by 8 to the 10th on both sides, I get 8 to the 10th, or 10 to the 8th divided into 200, which gives me a value of 2. times 10 to the minus 6. And the easiest way to see this, we could have 2 times 10 squared, bring the 10 to the minus 8th into the denominator, or out of the denominator into the numerator. We're left with 10 to the minus 6. So you learn to use those tricks that I told you about for exponents. Okay, now we shift gear from the common logs and do a couple of examples using the natural log. So the natural log involves using the lowercase e to the y. Remember, we called this the Euler's expression, E-U-L-E-R. So the example says e to the y is equal to 83. Again, we do just like we did with the common logs. We're going to take the inverse natural log, or we're going to take the natural log of both sides so that we have y times the natural log of e, which is equal to the natural log of 83. The natural log of e is just 1, okay? They're complementary. So we have y equals the natural log of 83. Again, put 83 into your calculator and push the natural log key. There's our natural log key right over here on the far side of the Casio, and we get 4.42. Solving for x, then, we're just moving the expression around so you get used to seeing it on both sides of the equation. 89 is equal to e to the minus x. So I take the natural log of 89 is equal to minus x times the natural log of e. Again, recall the natural log of e is equal to 1. So I have minus x is equal to a minus x is equal to 4.49, or x is equal to a minus 4.49 by moving to the negative sign to the right side of the expression. And finally, we have a value here that is, again, expanding the expression into a natural equation. X is equal to 20 times 1 minus e to the minus 0.5. This is really interesting because what this starts looking like is what we would see in a charging or discharging of a capacitor, and using those values of determining how much charge or how much decay we have on a capacitor. So x is equal to 20 times 1 minus 0.606 when we take the natural log, value, take Euler's value for 0.5 at a negative. X is then equal to the difference in those times 20, or 7.87. And again, that might be volts if we're doing a capacitor expression, which we're going to see a little bit at the end of chapter 23. In the last example here, we're going to say 5 is equal to 15 times the difference in 1 minus e to the minus 1 over x. Okay, so when we go through here and solve for these values, then we have 15 divided into 5 gives me 0.333 is equal to 1 minus e to the minus 1 over x. Now I can move my minus 1 to the left side of the expression and leave my e value on the right. I have a negative on the left, a negative on the right, so I end up with a negative value here that should have canceled out. That should have been e, I believe. I can check that. And we take the natural log of both sides, and I get 1 over x is equal to 0.405. Again, the negative signs cancel out, and I get x equal to 2.43. That should be what we have here in terms of the signs. Looks like I may have a negative error up on the top here. So chapter 22 has led us through the introduction of common logs and natural logs as tools for solving equations.